In this last video lecture of this series about the Lebesgue integral, we are going to pay our debts and give all the missing proofs, first to justify the axioms of the properties of Lebesgue integral for non-negative extended Borel functions, and then remind a few other general properties that we have stated last week and not proved either. Let us start from the axioms. So the integral is linear, which means it's homogeneous and additive. And let's prove these two parts separately. Okay, homogeneity means if f is a non-negative extended Borel function. Okay, so f is a non-negative extended Borel function. And alpha is a non-negative extended number, then we want to prove this equality here, that constants, even if they are infinite, they can go out of the integral. And this homogeneity, it will follow immediately from the definition. We just need to remember what's the definition. What's the definition of the integral of this function f? The mu, it will be the supremum of the integral of g the mu, where g is also non-negative, is bounded by f, and this is simple. And what happens if we put some constant alpha here in front of f? Well, then we're getting alpha here, and if we have a function g that is less than alpha f, well, assuming first alpha is not 0 and not infinite, and we can divide by alpha, then this means we can, or let's just replace g by alpha g, put alpha g and alpha g. So alpha g less than alpha f is the same as g less than f, and this alpha goes out because we have already proved homogeneity for simple functions. So this alpha will come out here, and the supremum of a set, we multiply that set by alpha. Well, the alpha also goes out. So you get the alpha here in the end, which is what we had to prove. This for alpha not 0 and not infinite. Now the case when alpha equals 0, there's not much to prove. This function is 0 for every omega. The integral of 0 is 0. And this will be 0 times whatever number we get here. This is still 0. So we are left with the case when alpha equals plus infinity. Now remember here, f is a non-negative function. So there are two possibilities. Either f equals 0 almost everywhere, or f will be larger than 0 in a set with positive measure. So the measure of this set is a positive. There are two cases. In the first case, if f equals 0 almost everywhere, it doesn't matter whether we multiply it by infinity, it will still be 0 almost everywhere. The only difference is that in the parts when it's not 0, now it will be infinity. But this set has measure 0, so this integral is equal to 0. And likewise, this integral is equal to 0 when we multiply it by alpha. Even if alpha is plus infinity, it doesn't matter, we still get 0. So this case is no problem. And now we have the case when the measure of the points where f is positive is positive. In that case, we have already seen an exercise in the first video lecture of this series of video lectures about integrals. We saw an exercise saying, in this case, this implies that the integral over omega of f the mu is not 0. And when we multiply it by infinity, we get infinity here. And likewise, whenever we get a positive number when we multiply it by infinity, then we get infinity. So this implies that the measure of the set where alpha times f equals plus infinity is also positive, and it is the same, in fact. And so we have a function which has positive, on a set of positive measure, takes values plus infinity. Then we can show that this integral becomes infinite using Chebyshev's inequality, but backwards. This we conclude that this implies that the integral of alpha f mu equal plus infinity. So also checks on this case. So we have proved, considering all different cases for values of alpha, that this homogeneity property holds. We now proved the second part of the property of the integral being linear. We have proved it's homogeneous. Now we need to prove it's additive. Additive means the integral of this function f plus another function h, so the function resulting from the sum of these two, equals, of course, the integral of f plus the integral of h. And well, let's prove this. So let's f and h be non-negative extended Borel functions. This is the case we are considering. We're proving additivity for the non-negative case. And well, we know from the previous video lecture that we have non-negative simple functions that converge in a monotone way to both f and h. Well, the sum of simple functions is a simple function, which means for each fixed n, this is a simple function, this is a simple function, and we can add them, and that gives us a simple function. And here it is. The sum of these two is a simple function. And we know the integral for simple functions is linear. In particular, it's additive. So we can split this. So if we ignore the limit, this equality here holds, because for each fixed n, this integral equals the sum of these two integrals. So this proves this equality here. And now, since this increases and this increases, and we know the limit of the sum of two sequences that are each one of them non-decreasing is the sum of the two limits. So this is also okay. And now we have to justify these two here, but for these two we just use the monotone convergence theorem. This function here, the simple function here, is non-decreasing, and in the limit it converges to f plus g. So here we can use monotone convergence theorem, and likewise here, for the same reason, we can use monotone convergence theorem here as well. And this proves what we wanted, that the integral of f plus g equal the integral of f plus the integral of g.